Okay, so last time we talked about modules and submodules and quotient modules over the ring, and we saw some examples, and that's pretty much where we stopped. Yeah. So we saw that if M is an R module, so our module was an abelian group together with a formula which, so our module was a triple like this, and this S gave you a formula for scalar multiplication. Yeah, so S was a map from R plus M to M, which satisfied some axioms. So I'm not going to repeat this since we did this yesterday itself. And then we saw that if M is an R module and N is a submodule, which means it's closed under addition and scalar multiplication, then M mod N is also an R module. Okay. So far things are very parallel to vector spaces. There is nothing new. Instead of field, you replace it with a ring, and instead of vector space, you replace it with module, and subspace by submodule, and even the quotient vector space by quotient module. So it's all parallel. There is nothing, no difference. Then we saw that we saw some non-trivial examples. For instance, if R is a ring, then R you can think of it as a R module as well, and then any ideal is a submodule of R viewed as an R module, and in fact, the other way is also true. Every submodule of R, R submodule of R is going to be an ideal. So it's pretty much the definition of ideal. Yeah. So here itself you can see there is some variation from vector spaces. So maybe example. So if you take R to be Z instead of a field, then there are many more submodules, right? For every ideal, you will get a submodule. But if R is a field, then there are no interesting subspaces of the vector space K itself. Yeah, there is either zero subspace or the whole space. But here you get a lot more submodules. So R equals Z, M equals Z, plus and dot, if you like. Then every ideal is a submodule of M. Yeah, so here itself you can see that something interesting is happening, and then you can of course see that. So if, for instance, we know what the ideals of Z look like. It's NZ. Yeah, example NZ, and some integer. Yeah, and then you can get many more Z modules. So then we also have Z mod NZ, which is so NZ is a submodule of M. So M mod NZ, which is same as Z mod NZ, is also a Z module with a natural action. Yeah. And we know what the action is. So in this case, you'll have an integer. Let's call it R in Z, and you have something here which is maybe denoted by M bar. Yeah. So our class, maybe we can incorporate this N part as well, and then R dot M. This is just Rm class of this. Yeah, so this was the definition. Yeah, so we use the notation R dot M bar is Rm bar, or we also use the notation R dot M plus NZ is Rm plus NZ. So we used various notation. So you can see that you get many more Z modules. Yeah. Just by taking just by using Z and submodules of Z, you can take quotients. In fact, for Z modules are more or less same as abelian groups. Okay, so there is no additional structure you have given. So it's more of a psychological thing. So modules, every module we know is an abelian group together with some scalar multiplication from the ring. But if the ring is Z, then the scalar multiplication is same as just adding that many number of times. Yeah. So the notion. So what I'm trying to say is that the notion of Z module is same as abelian groups. So every Z module is by definition an abelian group, and every abelian group has a natural Z module. Yeah. So what is that natural Z module structure? So let A, I didn't ask if you, everyone can hear me, yeah? The class is going fine?
Yes, sir.
Okay, good. Yeah, some issue with my daughter's class, so I'm a bit stressed today. Okay. Let A be an abelian group. Then A has a natural Z module structure. Z module structure, which is n dot A is just A adding n times if n is positive, or otherwise minus A adding n times if n is if n is negative. So absolute value of n times. Yeah. So that is what that is how you can give any A module any abelian group a natural Z module structure. Yeah, so as I said, there is some issue with my daughter's classroom. So you just go through this definition of linear map, which is exactly same as vector spaces. I'll be back in 1 minute. Yeah. Yeah, so okay, I'm back. So I hope you could figure this out. So this is exactly like linear maps in vector spaces. You want phi to be a map of abelian groups, and you want the scalar multiplication to work. So more formally, what it means is so here there are two actions of R on different modules. Here the first one R dot M, this one is action of R on M, and here the action is R on phi M. Phi M is an element of N. Yeah. So so if you want to write it very formally, then one has to write it this way. So the first S1 is a scalar multiplication on M, and S2 is a scalar multiplication on N. And this is how it works. Okay. So this is what our linear maps are. So here, yeah, so what else I wanted to say about, yeah, so I guess one can also write it in a more compact way. So, so maybe phi from M to N is an R linear map. So like in vector spaces, you can say that R linear map or R module homomorphism. Yeah. So this is also called R module homomorphism. Yeah. In a map, if phi of R M1 plus M2 equals R phi of M1 plus phi of M2. Okay, so this is one line way of checking whether if and only if you can, because there is a definition. So of course, if phi is an I linear map, then this holds, because I guess phi of Rm1 plus M2 is same as phi of Rm1 plus phi of M2, and then but because it's a group homomorphism, and then you can pull out a R because of this additional scalar multiplication condition from phi of Rm1. And of course, if this holds for all, so for all R in R, and for all M1, M2 in M. And if this holds for all R in R and M1, M2 in M, then of course you can take R to be 1 and M1, M2 to be arbitrary to say that phi is closed under addition. You can take R to be -1, M2 to be 0 to show that it's closed under inverses. And finally, you can take M2 to be 0 to show it's closed under scalar multiplication. Yeah, so this condition implies this one line condition implies that phi is an R linear map. Okay, so this is also parallel to vector spaces, nothing new about it. So most of the definitions are same, but somehow because the rings are more complicated other than vector spaces, the structure becomes more complicated. So the idea becomes slightly more complicated. So conceptually, it's richer. Yeah, any questions? Okay. So this. So let's maybe see one example or a few examples. So of course, some module. So one we have seen is that is M and R module and N a submodule. Then the inclusion map from N to M, which sends N to itself, yeah, is an R R linear map. So in fact, it's called injective R module, and it's also called injective R module homomorphism. Yeah, R linear monomorphism, R linear injective R linear map, or R module monomorphism. So there are many R linear map, also called R module monomorphism. Monomorphism is a word for injective homomorphism, and so on. So yeah. So then, of course, we had this. So there is not. I mean, there is not much to verify here, right? So of course, it's a group homomorphism, and since n is a submodule, r times n is so it behaves well. Yeah. So r times I of r times n is just r times n. So there is nothing to check there. Yeah. Which is same as r times I of n. Yeah, so it's because it's injective thing, there's nothing to check. Similarly, the map Q, so maybe I'll just write this as continuation. Q from the quotient map Q from M to M mod n. So recall last time we showed that M mod n is an R module with a natural R module structure. Yeah, and Q is a so this is a usual quotient map if you think of M and M mod n as groups, abelian groups. Yeah. So this is an R linear map. So we already know that, and this is in fact, it's an epimorphism. Yeah. So R linear epimorph, also called an epimorphism, R linear epimorphism. Yeah. So yeah, how do I do this? Yeah, so we have to, so we already know that this is a map of abelian groups. We only have to check R linearity. So maybe for Q, we will check the R linearity because our module structure is somewhat different. Yeah, here is just the restriction. Here is somewhat different. Yeah. So Q of, so we only have to check Q of R dot M is same as R dot Q of M. Yeah. So Q of R dot M. So for R in R and M in M, Q of R dot M is just by definition it is Rm bar or Rm R dot M plus N. Yeah. But R dot M plus N is same as R dot M plus N, and this is this was the R module structure on M mod n. Yeah, so this was the definition of R module structure on M mod n on M mod n. Yeah, which is same as R dot Q of M. Yeah, Q of M will be M plus N. Yeah, so we see that this quotient map is actually an R linear map. Okay. Then so these are some abstract example which you can make it concrete for any modules and so on. But you can yeah, so maybe time to see some more complicated examples. So I don't know. Yeah, so maybe let's. So as I said, the notion of abelian groups and Z modules are same. Yeah. So there is nothing. You won't get anything interesting if you're looking at Z linear maps. You'll just get abelian groups. Yeah, maps of abelian groups. So let's try to do something different. Yeah. So maybe this example will also consist of, so maybe we'll take some different eating. Yeah. So let's just take something like Z mod 5Z. Yeah. Or Z mod 6Z. Let's try to make things interesting. R is Z mod 6Z. Yeah. So can you give me an example of a R module? Z mod 6Z module. So one is Z mod 6Z, but maybe, and the other is 0, but maybe some other examples. Say that again.
So if we consider the whole module,
Yeah, so we can consider, so is,
module.
which module?
So if we consider a natural Z module and try to reduce it over here.
Natural Z module. Yeah. So I don't know. So will Z be a Z mod 6 module? So is, can you give Z a natural Z mod 6 module structure?
Z and natural Z. No,
Z mod 6Z is in.
Does Z have a Z mod 6Z module structure?
No,
So
sir.
Z is an abelian group, but can you make it into a Z mod 6Z module?
No, sir, not we cannot because of the characteristic or the properties of it.
Yeah, so the point is you have to do, yeah, so what if you want to do this, what will happen? So, you know, point is one of, so you try to, so let's try to do this, yeah, so this is probably a good exercise. So let's try to do this. So if we take some n in Z and some element in Z mod 6Z, so for instance 1, yeah, then 1 dot n has to be n, yeah, that is what one of the axioms of modules is. 1 of R times M should be this, yeah, for all n in Z, yeah, but that also means that and then some other axioms tells us that if we do this a few times, let's say 6 times or any number of times, then this should be same as n plus so many number of times, yeah. But so if this is 6 times, then sorry, dot n I've forgotten here, yeah. So then this becomes but if you add 1 6 times, then you get 0 dot n, yeah, the class of 0 dot n, because if you add 1 6 times in Z mod 60, you get 1, you get 0, and this is 6n, yeah, but this has to be 0, yeah, this is also some property which we saw, yeah, and 6n is not equal to 0, so this is a contradiction. So there is no there is no Z mod 6Z structure on Z, the abelian group Z. So the abelian group Z, you can't view it as Z mod 6Z module. Okay, so it does put some restriction. Okay. Okay.
Sir?
Yes.
Sir, any abelian group whose elements have order, whose orders divide 6? Elements whose orders divide 6?
Yeah, so you can take, yeah, so for, so it should be, so every element should have order which is a factor of 6, yeah, that's what you're trying to saying, yeah. So those
Yes.
those abelian groups you can give a Z mod 6Z module structure. So maybe let's take something like Z mod 6Z plus Z mod 3Z. Yeah. And so this we can give it a Z mod 6Z module structure. So how would we do that? So maybe I'll so you know how to do this, yeah? So AB is an element of M, then what you do is just take and R is an element of R, then RA, RB is an element of RA, RB is defined to be the usual thing, yeah? So A is represented by some guy, yeah? So A, so maybe I'll call it box A and box B, yeah? So, and this is box R. So this is actually 6, and this is 3, and this is 6. So this is, you take 6, and this is, again, you take 3. Okay, so so it's sort of, one has to check that everything makes sense, yeah? So it's well defined. So my definition is, sorry. So my definition is 6 dot A6 B3 is RA6 comma RB3. Yeah. So this is what the definition is. Okay, so these are some. So these are the abelian groups on which you can give the Z mod 6Z module structure. Okay. And yeah, so now I wanted to give you some maps from between various submodules and so on. So this M has some submodules, so you can take N to be the subgroup generated by let's say 1 comma 0, yeah, that 1 bar generated by 1 6 comma 0, yeah. So this then N is a submodule and you have you'll get some quotient, yeah. So M mod N, what is M mod N isomorphic to, or what is M mod N whatever, what is this quotient?
Z by 3.
Yeah, so it's something, but isomorphism we have, so one can show that this is going to be let's say isomorphic to Z mod 3Z. So we have already talked about linear maps. So linear maps are isomorphism if it's bijective as well, a linear map. Yeah, so maybe time to write that down. And our linear map of our modules is an isomorphism, is an isomorphism if it is bijective. So that you can take it as definition, or you can say that you can say that there exists a map in the other direction such that the composition is identity. So it so happens that they are equivalent in this case. And so this is some easier mod. So this is somewhat similar to vector spaces here, because I just took one component in some sense, yeah. But here you can also take submodule like generated by, let's say, 2, 6, and maybe 0, or let's just take 1. Yeah. So something non-trivial. So this so the submodule generated by these two. So this is okay notation for generation. Yeah. So and with the submodule generated by these two, then what? Or maybe let's call it N1. Yeah. Then what is M mod N1 isomorphic to?
So Z mod 2Z, direct sum 0.
Yeah, so it's just so you just look at it as groups first. Yeah, so as a group it is Z mod 2Z, direct sum 0. So so it's going to be naturally isomorphic to Z mod 2Z, direct sum 0, but that is same as is isomorphic to Z mod 2Z. So as abelian groups is isomorphic to Z mod 2Z, and we realize that this quotient is actually R linear. Yeah, so this is going to be an R linear isomorphism. R linear map. The quotient map is also R linear, and yeah. So this is going to be, and Z mod 2Z has a natural. So this has a Z mod 6Z module structure, and whatever that natural module structure is, that is what you get here. Yeah, so Z mod 6Z has a submodule which is it has a ideal generated by 2Z, and hence Z mod 2Z has an R module structure. Yeah. Yeah.
So, could you please explain why it's Z mod 2Z over here? Shouldn't it be Z mod 6Z? Because there are 3 elements in N1. So there should be 6.
Sorry. There are 3 elements in N1. So okay, so yeah, maybe let's just try to. So you are taking the ideal generated. Yes, sorry. So one should put, yeah. So that's why then I was trying to put this ideal submodule generated by this pair of element, and here this is submodule generated by this. So let's try to. So maybe this is not right. So let's just try to understand what this subgroup is, yeah, what this quotient group is. So yeah, so what is this quotient group? So what are the elements of the quotient group?
So for every element, we can find a representative with the second column, second element 0, and the first
2, 6, comma 1 is there, and yeah, so this is 4, comma 2, and 0, comma 0. Yeah, so these are the elements of this this submodule N1. Yeah, so of course the quotient should have 6 elements. Yeah, because the total number of elements is 18. So so what are the elements in the yeah, so it's going to look like so here the quotients will consist of yeah, so it's a bit more complicated to write the notation, yeah, but it's going to be yeah, so it has to be so it should have 6 elements, but what are those but is it yeah, so once it's 6 elements, it has to be Z mod 6C, yeah. So this should be Z mod 6Z isomorph, because there's only one group, abelian group of order 6, which is Z mod 6Z. Yeah. But notationally, maybe it's a bit difficult to write. Yeah. So one can write as yeah. So the so maybe I'll use the shorthand rather than these guys. So you write 1 bar 1 comma 0 bar is one element whose order is going to be, yeah, so this will have order 6. Okay, so this will generate. So you take 1 in the first component and 0 in the second component, and then 2 comma 0 is not in this submodule, so that's going to be so it's not 0, and then 3 comma and so on. Yeah, so this is this will be a generator for this thing. Okay, so this m mod n1 is sort of generated by this image of this guy. Okay, and the point is this is the only R module structure on Z mod 6Z. Z mod 6Z are module structure on Z mod 6Z. There is only one modulus. Yeah. Okay, so this is indeed Z mod 6Z. Okay, so let's so that is what else I wanted to do about before I get to isomorphism theorem. Okay, so I guess nothing else. So let's yeah. So yeah, I mean, I'll define kernel, and so first observation is that the kernel and image of a linear maps are also R modules. Okay.
Sir.
Yes.
Sir, could you explain once again that what you meant by that there is only one R module structure on Z mod 6?
Yeah, so you have to say what happens to one dot. So Z mod 6Z is a group, then so you have to say what happens to 1.1. Yeah, so 1 dot is and maybe we'll write it as generated. Yeah, so maybe it's generated by some element A of order 6. So 1 dot A, so that the notation is clear. Yeah. So what should happen to 1 dot A by definition of R modules? This has to be A. Yeah. And this determines the R module structure on Z mod 6Z, because then what you want to say what happens to 2 dot A. Yeah. So it has to be 2A. Or maybe if it's yeah, so if this is written additively, then it's 2A, yeah, and so on. So anything in the ring R, which is Z mod 6Z, this is how it's going to work out, yeah. And somehow if it's 6 dot A, then it's 0, because 6 is 0 here also, and so there is no contradiction. And if so instead of A, if it is 2A, and you want to know how does 1 act on 2A, that also is sort of determined, yeah, because of the distributive law 1,6 dot A plus A. Yeah, so it is there is only one way to do it, which is 1,6A plus 1,6A. which is just 2a. So sorry. So yeah. So 162a is anyway okay, but I meant if you want to. Yeah. So this works for everything. Yeah. So not just a, but any element, not just the generator, but for any element in Z mod 6Z, the structure is more or less determined. Yeah. By the same principle.
Okay, sir.
Okay. So you don't have to do it separately. So there is only one way to give a module structure on Z mod 6, Z mod 6Z module structure on Z mod 6Z, which is the natural one. Okay. So there is only one map from this to this satisfying all the axioms. That's what it means. Okay. Now the next one was about kernel and co-kernel. Yeah. So there you go. So let phi from M to N be an R-linear map of our modules. Then, so maybe this I can call it a proposition. Kernel phi and image phi. Kernel phi is an R submodule of M. Submodule of M, and image phi is an R submodule of. Yeah. So these things are easy to verify. Okay. So to check, so kernel phi definition is like abelian groups. Yeah. So kernel phi is a abelian group. We just have to check that it's also a submodule. Yeah. So let xy be in kernel phi. Yeah. To check that it's an R submodule, all we have to do. So last time we saw that it's enough to check that it's closed under addition and scalar multiplication, or like in vector space. So these two statements you can combine in checking that enough to check, enough to show, like in linear algebra, you must have seen, enough to show Rx plus Y belongs to kernel phi for all R in R. Yeah. But what is phi of Rx plus Y? So this is a shorthand of saying it's closed under addition and scalar multiplication. Yeah. So this is phi of R times phi of X plus phi of Y. So phi is our linear map, precisely means this, which is of course 0. R times 0 plus 0, which is 0 of N. So these are zeros in N. Yeah, so kernel phi is an R submodule of M. Similarly, you can check. So do you want me to check? Okay, let's just similarly xy is an image phi, and R is in R. Then Rx plus Y we want to show is an image of phi. So Rx plus Y is let's say R times phi of something. X is an image phi, right? So phi of let's say x1 and plus phi of y1 for some x1 y1 in M. Yeah, so xy is in image phi means there is some x1 y1 in M such that x is phi of x1 and y is phi of y1, and then you use the fact that phis are linear. So this is same as saying this is equal to phi of rx1 plus y1, which implies uh, image phi is in R submodule of N. Yeah. So maybe after the break, I'll write down the statement of isomorphism theorem. Okay. So let's just take a break, and then after that, I'll take questions. Okay. Are there any questions before I resume? Okay. So as you know that even in vector spaces we have this, that the kernel is a subspace and image is also a subspace of the range. And there is also analog of, I mean, since this theory of R modules is a generalization of theory of vector spaces, there is of course analog, there will be analog of isomorphism theorems as well. But isomorphism theorems are not very interesting in the vector space setup. Yeah, why is that? So it's sort of, the reason is that it's sort of easy to determine when two vector spaces are isomorphic. You just look at their dimensions. Yeah. So so there is something called rank nullity theorem, right? So that is so you express isomorphism in terms of dimension in some sense. So rank nullity theorem is an instance of an isomorphism theorem, but it's about some rank being equal to rank plus the dimension of the null space is equal to the dimension of the vector space. Yeah. Rank of the map and the kernel dimension of the kernel. Nullity is same as the dimension of the kernel. So that is how I mean, just knowing the dimension of various vector space, you can know whether the two vector spaces are isomorphic or not. But for our module, there is no notion of dimension of a module. Yeah. So so one has to. So it's a more refined object. So one has to have. So isomorphisms will not be determined by dimensions or some numerical value. Yeah. So, but these isomorphism theorem are similar to the ones which you saw for groups or rings, but much more simpler to write, because here the kernel is again a module and the image is module. There is no ideal rings like in rings, and like in groups, you don't have to check whether something is a normal subgroup or not. It's automatically normal, and always the quotient always exists. So so things are much neater in isomorphism theorems for modules. Yeah? So let me just state the results, and the proofs are very much similar to what you have seen earlier. Yeah. So first isomorphism theorem. So maybe there are various versions. So maybe I'll just write the most general version first, and then the corollaries are gives you the isomorphism. So let R be a ring. So I guess I had always said in the last class, all our rings are going to be commutative ring with unity. Let phi from M to N be an R module homomorphism. which is same as our linear map. Let K be the kernel of phi. So we know that K is going to be a submodule of M. Yeah, and let so I think I forgot to start recording. No, I did start recording. So recording is going on, right?
Yes, sir.
Okay. Okay, good. Yeah. So let K be the kernel of phi, and let's take some submodule of K. Yeah. So let's give that some name. So maybe n is there. So maybe K1 contained in K be an R submodule. So module of K. Now, of course, K1 is also an R submodule of M, because then K1 is also an R submodule of M. And what we want to say is that there exists a map from, there exists an R linear map let's call it phi tilde from M mod K1 to N, such that the following diagram, such that this picture will commute, yeah, such that Q1 from such that Q1 followed by phi tilde is equal to phi, where Q1 is the quotient map. So it's M to M mod K1. Okay. So maybe I should have just taken, I shouldn't have put a notation for kernel phi. I should have just taken K1 to be a submodule of kernel phi. Yeah, but it's okay. Yeah, so this is the first version of, so in pictures, what it means is you have M to N, this is phi, and we always have this quotient map, which is R linear, Q1 from M to M mod K1. So what this asserts is that there exists a, and this is unique, exists a unique so anyway, so there is a natural map, so there is going to be unique as well. And this is what is phi tilde. Okay, such that this diagram commutes. Okay, so what is the proof? So we just yeah, I just a bit worried about uniqueness, but this should be unique, yeah. So so we just first of all we construct phi tilde. Okay, so phi tilde of M plus K1, we have to define what it is, yeah, for M in capital M. So a typical element of M mod K1, it looks like it's something like this, M plus K1. You define it to be phi of M, yeah. So so this, I mean, we'll have to check it's well defined, because we are defining it in terms of representative. But what we are saying is that phi tilde composed, phi tilde of Q of M is phi M. Yeah, this is what we are saying. Right, so more or less by definition, this will hold. Yeah, this will hold. So this is how so the objective of phi tilde is to make this diagram happen. Yeah. So you define, you try to define it this way and just show that this definition makes sense, and then we will check that are linear as well. Okay. So of course,
sir, is it enough to check only the multiplication, because for groups we had such a theorem already?
Exactly. So we don't even have to. This map makes sense because for groups it makes sense. Yeah. So the only thing we sorry. So phi tilde is well defined, and a well-defined group homomorphism follows from the first isomorphism theorem for groups. Yeah. So the only thing you need to know is that what you are modding by is some normal is a normal subgroup of M contained in the kernel. Yeah, which is what we have in this setup. K1 is everything is normal because M is an abelian group, and K1 is contained in the kernel. Then this is okay. Okay. So the only thing one has to check is that phi tilde is linear. So we only need to check that phi tilde is linear, and that will complete the proof. So the uniqueness etc. also is from, I think uniqueness is also okay. Yeah, I mean that is true even for groups. Yeah, so this is also fine. So so what we'll do is just check that this is R linear. So that is also okay. So phi tilde R dot M plus K1. So we'll have to for R in R, for R in so for R in capital R, phi tilde R dot M plus K1 is by definition this is phi tilde of the this is how the R module structure on the quotient is Rm plus K1, which by definition is phi of Rm, which is R times phi of M, which but phi of M is same as phi of phi tilde of M plus K1. Yeah, so this is R times phi tilde of M plus K1. Yeah, because that's the definition of phi tilde. Yeah, so phi tilde is R linear. Okay. Okay, and the composition fact we just observed that this is true by definition, or you can use the group the first isomorphism theorem for groups. Okay. So that completes the proof for the version 1 of first isomorphism theorem. And like the other versions are corollary to the version 1, I'll just state the corollary, and the same proof works. Yeah. So as a corollary, let phi from M to N be an R linear epimorphism or R module epimorphism, maybe that's more appropriate. In epimorphism, that means it's a surjective or linear map. Then the induced map phi tilde from M mod kernel phi to N is an isomorphism. So the induced map coming from the previous version is actually an isomorphism. And that is because the map is now going to be both injective and surjective. Okay, so it's bijective. Okay, so I'll skip the proof because it's same as the one we did it for rings, or as you may have seen it for groups. Yeah. So that's first isomorphism theorem. Let me state the second and the third isomorphism theorem. And they are also, as we saw, they are both all corollary of the first isomorphism theorem. Yeah. So I'll just state them for record, and the proof is just copy the proof for rings or groups. So second isomorphism theorem. Morphism theorem. So so what is the second isomorphism theorem? So let M be an R module, and so third is easier to remember. Second is something I always M and N be R module. No, M be an R module, and we have some certain number of submodules. Yeah, that so everything lives in M. Yeah, so let N1, N2, and N3 be are submodules of M. So of M. Then yeah, so intersection of two submodule is a submodule is something which I should have stated, but maybe I will come here. I will do that here. So N1 plus N2 yeah. Okay, so what is the N1 plus N2 mod N2? Yeah, so maybe N3 is not needed. N1 plus N2 is a submodule of M, so I'll have to say what N1 plus N2 is isomorphic to N1 mod N1 intersection N2. Okay, so let me just modify this statement. N2 B are submodules of M. Then N1 plus N2 mod N2. So N1 plus N2 is the submodule is the submodule of M containing both N1 and N2, smallest submodule. And N1 intersection N2 is exactly the intersection, and it happens to be a submodule. Then the assertion is that these two quotient modules are isomorphic. So here N1 plus N2 is the smallest submodule of M containing N1 and N2, and so I'll give you another description of that as well. And N1 intersection N2 is also an R submodule of M. Okay. So maybe since there are some, so the isomorphism part will not be too complicated, but let's just look at these these objects, yeah, and conclude that they are indeed submodules. And then the isomorphism part, the proof is same as in the ring case or in the group case. So there also we had some ideals here, and we said that I plus j is. So there, I guess we had rings and stuff. So it was slightly more complicated, yeah. But here everything is a module, so it's slightly less complicated. Okay. So N1 plus N2. So one definition is this, but first definition is that is the smallest submodule containing this. Containing N1 and N2, so smallest submodule of M. But concrete description of this is N1 plus N2, where N1 belongs to N1 and N2 belongs to N2. Yeah, so its elements are precisely this. So first, so maybe it's not a proof, but more like a, so I'm not writing the proof right now, but some observations about ingredients needed to state the theorem is the smallest R submodule of M containing N1 and N2. So of course, the set we have defined here obviously contains N1 and N2, and so if you show that this set is an R submodule, then you are pretty much done, because any submodule which will contain both N1 and N2 will contain in some of these two elements as well. Yeah, so it's enough to check that N1 the set is indeed an R submodule. So this is of course closed under addition because of the way it's defined, and also scalar multiplication. Yeah, so easy to see, easy just by inspection, visual inspection, easy to see. And this set N1 plus N2 is maybe take this as the definition, is closed under addition and scalar multiplication. Addition and scalar multiplication. So just so if you have N1 plus N2 comma N1 prime plus N2 prime, two elements of the set, then N1 plus N1 prime is in N1, and N2 plus N2 prime is in N2. So the whole sum is in there, yeah, is of this form. And scalar multiplication as well. R times N1 plus N2 is same as Rn1 plus Rn2, and Rn1 is in N1, and Rn2, R little n2 is okay. So that is okay, and let an alpha be R submodules of M, alpha is in some indexing set. Indexing set. So it's true even for arbitrary number of submodules. Then intersection n alpha in omega is an R submodule of M. Yeah, because of course it's going intersection of arbitrary number of subgroups is a subgroup, so it's a subgroup, and R linearity also you can just check. Yeah, because R times n will belong to each of these n alpha, and hence it belongs to the intersection. Okay, so once these are defined, then of course the rest is easy. You give a map from maybe n1 to n1 plus n2 mod n2, and then check that the kernel is, show that this is surjective, and then check that the kernel is precisely n1 intersection. Yeah, like we did it in the case of rings. Okay, and finally, I'll just state the third isomorphism theorem because that's the easiest to state, and then we will call it a day. Okay. So, third isomorphism theorem. Let M be an R module, N be an R submodule of M, and K be an R submodule of N. Then we have this isomorphism, so you can do M mod N, and this is going to be isomorphic too. So if M is K is a submodule of N, then K is also a submodule of M. So you can look at this quotient, and then one has to show that N mod K is a submodule of M mod K, and then the quotient is isomorphic to this. So one checks that N mod K is a submodule of M mod K. Yeah, so there is like ideals in R mod I are in bijection with ideals of R containing I. So same thing is true about module submodules of M mod K. It's in bijection with submodules of M containing K. Okay, so and the proof again is sort of straightforward. So I'll skip all the proof of isomorphism theorem since we already did it for rings. Okay, so that's it for today. Are there any questions before we disperse? Okay, so if there are no questions, let's disperse. Okay.